Hello Internet, today we're going to talk about try.net. So try.net is published by Microsoft. It's a basic C# sandbox effectively. So you get a web browser effectively that can be a text editor, or code editor rather. And so you can write C# programs and actually run them online and see what the results are. So we're just kind of play with this. I think we're going to solve the Fibonacci problem and look at like some dynamic programming issues. But we're just going to explore this and kind of introduce it as sort of a way to work with this. It does work on phones as well, but that can be a bit hairy. So we're going to do this on the desktop. And so this is sort of what you'll start with. They'll actually have a sample program for you. I've deleted that. This is pretty much the basics you can get for like a basic C# program. We actually don't need link, so I can drop that. We don't need that. So this is our program. It does nothing. If I run it, we don't get anything. But that's by design. The cool thing is we can get things if I do say console.writeLine. And you'll notice we do get IntelliSense with this, which is pretty cool. We get all these help things and all this other fun stuff. My understanding is Microsoft is working to integrate this in with their documentation. So what that means is that you are actually, all those code documentations you see on MSDN, that's all going to be in this, which means you're actually going to be able to edit and run those code samples. In this case, we have just hello world, the most basic you can get. We've got our program up here, and then we've got the output down below. And so that's the basics. So all you have to do, hit run, it compiles and runs it, and that's pretty much it. So what we want to do is solve Fibonacci. So Fibonacci goes 1, 1, 2, and it's just the sum of the previous two numbers in the sequence. So it can either start at 0 or 1. If it starts at 0, the sequence starts with 0, 1, 1. If it starts at 1, it goes 1, 1, 2, and so on. And so traditionally, the different definitions mean index 0 is 0. But some Fibonacci sequences, especially historically, have started at index 1, so that 0 was left off. So what we need to do is sort of define Fibonacci. We're going to do this recursively, and then we're going to show why that's not the greatest idea. So Fibonacci is going to be a public, we're just going to stick with static methods for now, and I just want to return an integer as our Fibonacci. So we're going to just say, get us the Fibonacci number for an int index. So given an index, we want to get a Fibonacci number back. And so there's two things to do when you implement a recursive algorithm. You want the exit of that recursive algorithm, and then you want the recursive bit. So recursion is just invoking the same function again. So a recursive function is a recursive function, which effectively means I go like this, and a basic example would be, say, index minus 1, which effectively means I'm calling the same function again with slightly different inputs, so I get a slightly different result. And so we know that the result of Fibonacci, the Fibonacci value at an index, is equal to the previous two results from that. So it's actually equal to Fibonacci minus 1 and the index minus 2. That's the basic definition of what Fibonacci is. So index 3 would be 2, because index 1 and 2 are both 1. So it goes 1, 1, 2, where 2 is the sum of 1 and 1. And actually that works for the first one, or the second 1 as well, where 1 is the sum of 0 and 1. And so it just kind of keeps going. So let's assume that you can actually have two results, or not two results, but let's actually assume that you start at 0. So 0 is a valid index, which means if our index is less than or equal to 0, we're going to assume anything less than 0 is just 0. We want to return 0. So 0 is the sum there. Otherwise, if our index is equal to 1, then the result is 1. And so now oh, that's not how you do that. There we go. Let's actually return. So now what's happening is if my index is less than 0 or is 0, we get 0. So index 0 is 0. Index 1 right here is now 1, which means we have 2 lower bounds, which means this function effectively ends. So if, say I plug, ooh, that's not right. Let's say I plug in 2 here. If I plug in 2, we get index at 2 and 2, which means we're effectively getting 1, which will hit this code and return a 1, and 0, which is going to hit this code and return a 0. So index 2 is just 1. If I plug in a 3, we do that again and get the recursive results. That's the point of a recursive function. It just keeps going. And so this has some problems. One of them is recursive solutions don't scale well, especially when they branch like this. And so one of the ways to fix that is dynamic programming, which we'll get to. So let's say I want the first 4, let's take the first 10 numbers in Fibonacci. So for int I from 0 to 10, let's just increment over that. What I want to do is then print those out. So we'll just write them on their own separate line and just do Fibonacci of the index. And so we should be able to pretty quickly verify that this is correct. If I run this, it can take a little bit. There's some really cool stuff going on in the back end. They kind of fixed some of it so you can't have as much freedom. File IO and stuff, it doesn't work anymore. But we can kind of verify that this is working. So what I should see is say 8. 8 should be the sum of the 2 numbers above it, so 5 and 3. 3 should be the sum of 2 and 1, and so forth. So this looks correct, which is good. The problem is that took a while. And part of the reason is this is all running in a whole bunch of virtualized equipment, but it gets even worse if I start increasing this. This may actually take a really long time. I'm only trying to find 100 Fibonacci numbers, right? That actually didn't take that long. But we actually lost some input. Oh no, can I not go up? Well, that's unfortunate. Maybe there's a scroll bar that I'm missing. Doesn't look like it. Okay, that's new. I've only really seen this, so I wasn't really expecting that. But it looks like we're, oh no, never mind. This all looks correct. It's just, it's cutting things off. Anyway, not really relevant to what I'm talking about. The point here is this is a very inefficient algorithm. This is going to be super slow. And so part of the reason this is really slow is, let's say I take Fibonacci of I. Say Fibonacci is 100. So if I do 100, I then need to calculate 99 and 98. Now, if I do both of those, I need to calculate those too. So I need to calculate 98 for 99 and 97 for 99, plus I need 97 and 96. And so this kind of shows you the problem here. We haven't really gone that far down this, but we're already sort of exposing an issue. We've now solved for 98 twice and 97 twice after only three recursions. And this only gets worse. Now we need to do this 4 times. So I need to do 97 and 96 and 96 and 95 and 96 and 95 and 95 and 94. And this sort of shows you the problem. It's growing exponentially. So the deeper I go in calculating Fibonacci numbers, if I try to do 1,000, we would need to do 1,000 squared calculations effectively, which is a lot. that's like a million? Yeah, million, right? I think my math is right. Doesn't really matter about the math. Point is, this isn't good. We can fix this. One of the ideas, dynamic programming is effectively the idea of using something you've already solved to help you solve the current problem. And so what we can do is if we save, the result for 97. We calculate 97 and we save it. Then we can just reuse it. So instead of referencing this each time and recalculating it, we can say, I've calculated 97, here's the answer. And so the easiest way to do this is just by storing it in an array. So let's do that. Let's do a private array list. This isn't going to be included, so I'm curious how it's going to handle this. I don't think it's going to import it. So we may see some problems here, but this is going to be our Fibonacci. Is that spelled right? That might not be spelled right. There's a reason I used fib in the other one because I don't really remember how to spell this. So Fibonacci calc results. Sure. And we'll just create a new array list. So we're using an array list here because an array list is backed by an array. There's two basic types of arrays or of lists. There's the array list, which has effectively a indexed set behind it, which means you can look into each specific index and get the result, sort of like we're doing here, hint hint. The other one is a linked list, which is effectively a series of connected elements, so every element kind of knows the next one to point to, which means you can have things kind of scattered all over and they kind of just say, go here, go here, go here. And it just kind of goes like that. Array lists work better for what we want because it allows you to get the element out in a constant time, which is what we want. So if I say I want index 1, I want to be able to get to index 1 as fast as possible. And so array lists solve that problem the best. So we have this now. But what we need to do is, before any of this, we need to actually solve for some of this. Actually, let's plug in our first two values. I think this is valid. We'll find out. Also, I lost the run button. When I did that giant print statement, it's gone now. That's interesting. I don't know what's causing that. Let me copy this and refresh. Hey, look, it's back. Oh, hey, look, it starts with Fibonacci. I probably should have checked that out first. Oh, well, I actually wasn't even paying attention to that. That's unique. So my result, or my implementation, is going to be different than theirs. They're using link, I think. But regardless, we have this. I should be able to run this. It should break, right? Because it's not going to find array list. That's the expectation here. Array list is in system.collections, I believe. So this should throw an exception, and we should be able to debug it. Kind of feeling this out as we go, because I have only partially looked at this. What? Okay. That's almost more concerning. I got nothing. No exception, no error. That's interesting. I wasn't, of all the things that I was expecting, that wasn't it. So, okay, this is more what I was looking for. The typer namespace name array list could not be found, which means we need to include it. Does it give us the actual suggestion? This is going to be coming straight out of the C# compiler. So these error messages are going to look the same whether you're in Visual Studio or here. It's the same stuff. So if I do system collections, it actually knows what stuff is available, which is good. We should be able to run this, and no, cannot be. Generic. Got it. So when .NET originally came out, they created collections, and then they added generic types. Generics weren't added until .NET 2, C# 2, one of those two. Anyway, they came afterwards. So there's actually some really fascinating papers about how they came about. But anyway, getting totally lost. The typer namespace name array list could not be found. I'm doing Java stuff. It's just called a list in C#. Keep in mind, when somebody says list, they actually mean array list. A linked list is the alternative. List just doesn't have the backing type on it. It's an array list. So we now have a array list with the first two results. So what we can do is get rid of this. We no longer need either of these, because what we can do instead is say if our Fibonacci results length count. Yeah, I always get confused between this and Java now. If the count is greater than the index, then I can just return that index from it. So the value at that index. So I can just do this dot index. We've already calculated it, just feed it out. We don't need to go any further. If this works, we should get this again. If I rerun this, the values here should stay the same. If they don't, we screwed something up. So an object reference is required for the non-static field private static list. Got it. We're doing static stuff. Okay, it's all the same. 0, 1, 1, 2, 3, 5, 8, 13, etc. So that means that all worked. The problem is that only works for the first two elements. We need to pre-compute everything. So we know that our calculated value, yeah, this will work. Our calculated value is equal to the sum of the next two elements. So then I'm trying to think if this makes sense. I think it does. Yeah. Sorry, I'm going down a... I think this is all I need to do to get this to work, and I'll kind of walk you through why. I believe if I calculate this, let's say I get 4. So I get index 4, which would be 3. That's going to have to calculate the sum of index 2 and index 3 and index 1. 2. Index 3 and index 2. So we're going to get 2 and 1. Those both get calculated prior to everything else, right? So this is backwards though. So as long as I get the order correct, as long as I do, actually this doesn't matter. Doesn't matter. So as long as everything before this number got calculated, if I just add it, it will be the last thing on the list. So effectively, let's say I want to calculate 3. In order to calculate 3, I need to calculate 2 and 1, which means both of those need to get added to our list before this is done, because that's what this is doing. So those already exist. If they don't exist, they'll get added. So as long as they get added in order, I don't need to insert them at a specific index. I can just put it at the end. I think I might be making this more complicated than I need to, but that's the gist of it. So anyway, the other alternative is you could just do an insert, and I believe this takes an index, so I just insert it at the index like this and run this. Not do that. Yeah, it takes it in the other direction. So index would go here. And then the calculated value goes at the end. And we lost our run again. Great. That's weird that keeps going away. I feel like that's not supposed to happen. Well, let's rerun this. Are they caching this? No, it doesn't look like it. Yeah, they do, but it doesn't So the difference between their solution and mine is mine will cache it for multiple iterations. So if I re-invoke this, it will still work. Theirs persists the value and sort of creates an enumerable list, an infinite enumerable list of this, which does the same stuff, but it doesn't persist it. There's no memory cost necessarily, but it's not persistent. Anyway, different implementations, different reasons to do them. So this should still work, right? Yeah. So inserting works now. You can use insert, you can use add. Both should work because, like I said, add means you have to calculate them before. If you change this, the insert or the add is not going to work anymore. If you start like skipping things or change that definition, it doesn't work. For Fibonacci, it's fine. So that's Fibonacci and try.net. Mostly try.net. There's a few quirks, but it works. You could do file IO. I don't think you can anymore. They kind of, well, I think you can, but you only have limited stuff. You used to be able to see the entire Docker image this was running in. You can't do that anymore. I don't, unless they've changed it again. But that's something for another video. So this is like the basics of something on try.net. It does work on your phone. I did test that. At least on my phone it works. My Lumia 950. But there's a lot. It's not optimized for that. It doesn't work great for that. So you can try it. It might work. But I don't know, for just scratching out code or doing like quick demonstrations without needing to install anything, this is great. And I like the way that they're taking this with documentation. It's going to be handy, especially if other people start adopting that. If this becomes something that I can put on my site, for example, and you guys can take some of my code samples and use that, that'd be super cool. So I'm curious where this is going to go. But that's it for this video. So let me know what you think in the comments below. I'd love to hear your suggestions, your thoughts, or just random feedback you have for me. If there's anything else, let me know about that as well. But that's it for this video. So until next time, see you, Internet.